Let's dig deep into some of your other work. I feel a lot of this centers around the theme of generalization and making sure that robots can adapt themselves to different environments. You had a paper called Amplify that you
Yeah,
shared with me. Uh, what is the key goal here?
right. So this work has almost the same motive as Rakota does, and that's sort of alleviating the data bottleneck in robotics. So typically, we can only leverage this sort of expensive direct robot annotated data, like I alluded to before. We call that demonstration data. What Amplify does is it relaxes this assumption and explores how we can use different sources of data. One being videos of humans or videos of robots acting in the world with no action annotations. So we're not tracking hand pose or anything like that. We're instead just observing motion in pixel space. And then the second source of data is what we call off-task data, which is essentially the same as demonstration data, except there's no specified goal for the robot to achieve. So this could be robotics data on a task that you're not actually going to be testing on. So it could be a different embodiment, or it could just be also what's called play data, which is just acting in the environment in reasonable ways with no given goal. So what Amplify does is it leverages these two types of data in order to, again, expand the size of the data set. But the methodology here is different. The way that we leverage these sort of three sources of data, so we also have demo data, that's the third source. The way we leverage this is by breaking down what's called behavioral cloning into multiple modules. The first module is a forward dynamics model, which predicts the future observations conditioned on language. So you can imagine this sort of like video prediction, except we do something slightly more, I'd say, efficient. And then the second stage is called inverse dynamics, where given the next state predictions from the forward dynamics model, we predict what actions would be needed to cause those states to happen. Yeah, so that's the high level of it. There's more detail we could go into with how we capture states in motion and that kind of thing.
Yeah,
That's
yeah.
it.
So what you're saying is you're pretty much eliminating the need for any kind of action labeling on data sets. I could feed thousands of videos to to a robot, YouTube videos, and it could learn juggling, for example.
Yeah, in principle, it could. Although there's one caveat. So for the inverse dynamics model, we do need action annotations because the goal of this thing is to sort of map evolution of the environment to the actions needed to create that change in the environment. But what's nice is we need a lot less action annotated information than you would otherwise need. And we showed this in our results. The thing I'm most proud of from this paper is we're able to execute tasks that we don't have any action annotations for that specific task. So we have some action annotations, but they're for other tasks. So you call this a task generalization. And to my knowledge, we haven't seen anyone else do this for that particular benchmark that we were training.
What kind of tasks, by the way?
Yeah, so most of the tasks here, so I'll say the benchmark is called Libero. It's a set of 130 different tasks. Most of them end up being pick and place, which is kind of typical of robotics. But there are some more interesting tasks there too, such as turning an oven knob, opening a drawer, putting a book in a shelf, sort of like more precise than just pick and place. Things like that, yeah.
I But pick and place is not trivial. I mean, people think pick and place is really easy, but I'm sure you would agree that's pretty much 90% of the tasks involved in robotics.
Yes, and it's not a solved problem. Many people have claimed it's solved. Yeah, there's a lot of complication to it once you start trying to make it like a task-oriented grasp or task-oriented placement.
What is this conversation around long tails in terms of a lot of actions are context dependent and they can get complicated really soon. Even a pick and place task, it really depends on where you are, what you're doing. Can
Yeah,
you talk more about that?
absolutely. So one could claim, like I feel like the way a lot of people think about robotics is, oh, how hard could it be? You just go up to the object, you close the gripper, you go to the target location, and you're done. And I'll agree to some extent. You can do that to solve a lot of problems. But like you alluded to, there's this whole long tail problem where the majority of tasks are actually quite rare. Not the majority, but the majority of effort will go into tasks that are quite rare. And you can draw the analogy here to autonomous driving. The analogous question here is, how hard could it be? You just have to follow the lanes. If you cross over the left lane, you turn right, and vice versa. And sure, you can solve this problem. Like one grad student in a week could probably make a lane following algorithm. But you run into these edge cases all the time. What happens if a trash can falls over on the street and you have trash everywhere? You need to avoid the sharp bits and hit the soft bits. And similarly for robotics, what happens when you're doing the dishes and you drop the plate and it shatters everywhere? Do you grab the broom? Do you tell your owner or the human what happened? There are all these edge cases, and even for grasping, something as simple as grasping. You don't want to grasp in the wrong place. Say I'm grasping a water bottle, but the lid is off. I probably don't want to grasp it by the lid. And there are constraints now. I don't want to turn the bottle 90 degrees. That's one example. But it's a very tough problem, and I think it's going to take a lot of effort.
Do you intend on solving it? What are some steps that we can take?
Yeah, I mean, I want to contribute to the solution for this. The most direct thing to do is to scale up the data. But the counterpoint to that argument would be this has not worked necessarily, or the problem's not solved for autonomous driving. I like drawing the analogy here because it's sort of like the same paradigm as robotics, but pushed further ahead in time. So I think more data is part of the solution here. I'm also quite bullish on reasoning, and that we need to, in my opinion, sort of start interpolating between low-level actions and high-level language. Language models are quite capable of robustly solving problems nowadays, at least in the realms of of math and coding. And I think they could do something similar when it comes to robotics. I would say if you tell ChatGPT or DeepSeek or whatever, if you tell them, if you tell it, I dropped the plate, what do I do now? It'll come up with pretty reasonable solutions, 3 or 4, one of which is probably correct, like sweep the floor or what have you. And I think if you connect this to these sort of behavioral cloning models, which learn how to predict actions given observations, I think that'll give you the robustness, at least this is part of the solution, to sort of generalize to these unseen situations.
Okay. Yeah. I want to get back to Amplify now. Thank you for
Sure.
indulging me with this
Of course.
tangent. But what is an actionless motion prior?
Yeah, great. So let's get into the nitty gritty. The way that we predict future states for the 4 dynamics model that I talked about is we actually track locations in the image and we predict where they're going to move in the future. So what we call this actionless motion prior is a way of compressing the actions into a discrete latent space, similarly to your vocabulary for a language model. You only have like 100,000, 200,000 words that you can choose between. In the same way, we break down motion in the video into a set of discrete tokens that we can auto-regressively predict, very similarly to a large language model. So in order to learn these tokens, we use what's called a variational autoencoder, which is just a way to compress and then decompress these sort of key point trajectories. Yeah, so that's how we learn the tokens. Once you learn them, you predict the future locations of all the points. I should specify we have this 20 by 20 grid points in the video. Each of those points, for the next second or so, we predict where the point's going to move given the depth. Yeah.
What is the key point trajectory?
Great. Yeah. So I should be more specific here. So a key point, we can say, is just a location in the first frame of a video. Okay. So we can specify, X equals 100, Y equals 252, whatever. And there are these nice off-the-shelf point tracking algorithms that we use to get our ground truth. And by point tracking algorithm, I mean, you give it the same initial points, but you also give it the entire video, the entire feature, and you track the points as they go through space. And what's really nice is that there's some recent models that have been released. The one we use is called CoTracker, and it's quite robust. It can deal with occlusion. So if your point moves behind an object, then it'll continue to track it. And if you move the camera around, it's quite robust to this.
So how does all of this translate into understanding what the action was and how to perform it?
Right. Yeah. So our key intuition behind using these key point trajectories is we think they encode a lot of action information. You can ask, what is an action? Typically in robotics, we parameterize actions by gripper delta gripper pose. So how does the translation and rotation of a gripper change from time step t to time step t plus 1? Our intuition behind using these key point trajectories is you have enough information in these like pixel trajectories, these key point trajectories, to unambiguously predict the action that corresponds to those trajectories. And that intuition turned out to be quite true.